Okay, so I guess the last thing to do this week is to introduce what we're going to talk about more next week, which is the integral method. So we've talked about correlations, and these are super useful for situations where solutions exist, right? So common boundary layers, so simple ones where temperature is constant or heat flux is constant, and shapes that are simple and common. All those things you would go look up the right correlation. Integral methods are what you would sort of resort to along with things like CFD methods if you encounter a situation where there is no correlation that you can use, and they're nice in that they're very flexible. So you'll find out that some of the things you can do with integral methods are you can deal with surfaces or boundary layer situations where maybe the temperature of the surface isn't constant, or the heat flux is prescribed in some weird way, or maybe even you have something like transpiration going on, or viscous dissipation is important. So all these things you can include in an integral method, whereas you'd be hard pressed to find a correlation that would deal with that kind of a situation. And so that's why these things are important. Today we're just going to give kind of an overview or an introduction, and then next week we'll dive into more detail about actually using these techniques. So the basis of the integral method is the integral form of the boundary layer equations. So we'll come back to these, but basically we're going to take our boundary layer equations, which are our simplified governing differential equations, and we'll integrate them across the boundary layer. So we'll integrate the x momentum equation across the momentum boundary layer, and we'll integrate the energy equation, again simplified for application in the boundary layer, across the thermal boundary layer. And that's what these two equations are. We'll come back to these, but these are basically integral equations, right? You can see these involve integrals of velocities and temperatures across the boundary layer. So from 0 to delta sub t and from 0 to delta sub m. So the way that these work then is you follow these 4 steps. And the first step is you assume a functional form for the velocity and the temperature, right? And so this is kind of interesting. You are assuming that you know what u over u infinity looks like as a function of y over delta sub m, right? And obviously what you assume here will impact how accurate, how realistic your solution finally is. And you can go everywhere from very simple, where you assume u is just a linear function of y, which isn't very good, and you'll get an answer that's not very accurate. Or you can go to something a lot more sophisticated, where you have a third order polynomial or something like that, where you've got all the right curvature and you can make it do more realistic things, right? So this is what makes these things only approximate, is that you're making these assumptions for these functional forms. But once you've made those assumptions, right, and you would assume a certain kind of form for laminar flow, you'd assume a different kind of form for turbulent flow, but you take those assumptions and you substitute it into these integrals. So everywhere you see a u or a t, you would substitute your function and you would carry out the integration. And what that does then is it leads to ordinary differential equations for the boundary layer thickness, right? So these boundary layer thicknesses sort of pop out at the end. There was left after you do the integrations, and you have ordinary differential equations that describe how these boundary layer thicknesses grow with x, right? And so they are ODEs, and so you can solve them in any number of ways. If they're simple enough, you can solve them analytically. If they're hard, if they're more complicated, you can solve them numerically. But the outcome of that ought to be some knowledge of how the boundary layer, the momentum boundary layer, must grow with x, and how the thermal boundary layer must grow with x. And as we talked about before, knowing the boundary layers lets you know the engineering quantities of interest, right? So you would know things like the shear stress and things like the heat transfer coefficient or the heat flux as a function of position. And so that's the steps that you would follow. Again, these things start with the integral form of the boundary layer equations. And just to reiterate, there's no magic here. We would literally take our x momentum equation. So up here we have our x momentum equation for a boundary layer. We integrate it from 0 to delta sub m, And we do kind of a lot of algebra and some non-intuitive math tricks. So all these steps are laid out in the book, and there's nothing in there that's super profound other than just kind of knowing what substitutions to make. But if you make all those substitutions, you end up with this equation right here. And honestly, you might be interested in knowing where this comes from, what these steps are. You certainly aren't going to be responsible for being able to do them yourself. And you would start with this integral form of the boundary layer. I want to point out a couple things here. This looks complicated. If you go from left to right, you can sort of see where these different things come from. So this first one is basically the rate at which the momentum of the boundary layer is changing, and then it's related to this is the force, the pressure force. It doesn't look like a pressure force, but it is. That free stream pressure gradient is related to a free stream velocity gradient according to Bernoulli's equation. And so this is actually the pressure force exerted by the free stream in a lot of cases, or at least some cases. So for example, for a flat plate, if U infinity is constant, then this term is going to be 0. But we'll keep it here because it's a lot easier to remove it than it would be to add it if we didn't have it here. This term here is related to momentum that's actually injected at the surface. So you can see this is V at y equals 0. In almost every problem, this would be 0 because you're not usually injecting fluid at the surface, but you may be dealing with some situation where you have either suction or transpiration and you want to consider that. So this technique would allow you to do that. And then this last term here is related to shear force. So there's a shear force at the outer edge of the boundary layer and then the shear force at the surface. And usually the shear force at the outer edge of the boundary layer is 0 because usually that's where the velocity gradient is 0. But we'll keep that just in case we have a shear-driven flow. So if we're dealing with a typical flow, like flow over a flat plate, we might not have the pressure force. We certainly wouldn't have any transpiration or suction, so that term would go away, and we wouldn't have any shear force at the outer edge of the boundary layer. So you'd end up concluding that the momentum change of the boundary layer is related to the shear stress at the surface. But all these other terms we can consider, right? And that's what makes this technique so powerful. And we have the same kind of thing going on for the thermal boundary layer. So we have the thermal boundary layer, again simplified for application the energy equation simplified for application in a thermal boundary layer. That's what this top one is. And then we integrate it from 0 to delta sub t, and we do basically the same steps, the same algebra, and some of the same non-intuitive math tricks, and you get down to this integral form of that equation. And again, this is where we'll start, and this is also, again, more complicated than it would typically be because we've kept all of the terms so that if they happen to be there, we can just keep them versus having to rederive them. So if we go through this first term is the rate at which enthalpy is changing in the boundary layer, so the rate at which the energy carried by the fluid is changing, and that enthalpy change can be driven by maybe we're injecting energy at the surface due to transpiration, right? So that's this V at y equals 0 term again, which will usually be 0 but might not be. Maybe we're adding energy by conduction at the surface or by conduction at the outer edge of the boundary layer, and this, like the shear at the outer edge of the boundary layer, is likely to be 0 in most of the case. And then we might be generating thermal energy due to viscous dissipation. So this is going to be our starting point. So next week, when we start on Monday, we will actually start to look at these steps and how to actually solve some problems using this technique. And we'll solve a problem that we already know the answer to. So we'll solve a problem for flow over a flat plate because we know what the answer is and we can see how close we get. And then we'll also look at, how we can use this to solve problems that are maybe otherwise unsolvable, which is obviously why we're learning this stuff.